Okay. Let's start. Sharing. Okay. I'll send you this little glossary since you can have sometimes some problem, and then also you see intensity sometimes it's defined as intensity power per unit areas. Other times it's a power per unit solid angle. It's inside the same physics. The several branches sometimes have some different, small difference in meaning that can be quite confusing. Luminosity, at least, it's clear. It's the total energy emitted per unit of time. So when we are talking on luminosity, we intend all the energy that's flowing outside the star or inside the star at a certain level. An internal luminosity and certain radius means that if we take a radius of some value in that through that surface flow this amount of total energy. Power, okay, is the energy per unit of time. Here are putting the measurement unit both in international system. So power are watt, joule per second. Also in CGS system that is quite used in astrophysics. They are erg by second. CGS is centimeter gram second. That is used for principally also because easily density are 1 gram or centimeter square to the cube and so on. So it's a common, it's not standard, but it's what is common used usually in astrophysics. Flux in a little that seems easy because it's the effect of a pier to pass or travel through a surface, real or abstract. In this case, surface of a star or surface has a certain radius, but is also a little problematic because can be the transportation phenomena of the vector. So can be the flow or the surface integral. The surface integral in this case should be the luminosity. That's the reason why sometimes it's some also you see in sometimes flux it means some unit per unit of area, and sometimes you consider all this unit flowing through a surface. Like luminosity is a flux, is flowing, so a flux on energy, but is not by unit of area, or directly what is usually called the flux, that is luminosity by area. I put it because, yeah, one can be a little confused, and there is a reason. And luckily, sometimes we use a word for two little different meaning. Just to remember the mean free path, that is average distance between essentially two collisions, to this impact that are changing energy, momentum, or other physical characteristic. And briefly, four main constants that quite used: luminosity, solar mass, solar radius, and the solar effective temperature, both in international system and CES system. Also, because usually, as I say, in astrophysics, it's used the second, even if legally should be used the first. I think also the paper should be using international system, not the CES. Okay. Let's go. I think I also sent you that was a nice resume of the constant. Some approximation, someone are definitely constant because in the last since 2019, the Planck constant, Boltzmann constant, the Avogadro number are fixed. Now that one are fixed to determine the kilogram. That is now is not more connected with the sample, but is connected with the Planck constant. But okay, this doesn't matter. Today we start to talk about the nuclear reaction and see all the process, the theory behind them, the description, and then we see the reaction, nuclear reaction that are happening inside the stars. The most famous, the secondly most famous, we'll see also someone that is usually not talked about, but are really talked about in the paper as the product. Mainly, it's if you do a rapid calculation in mean energy production for mass in a star. For example, the sun, we directly divide the L luminosity by the mass. We get that is approximately 2 erg by grams per second. This is obviously a really low level value because we are considering all the mass. The real value that is the energy production per unit mass is higher. This is also because you have to divide the luminosity that is energy produced completely the nuclear reaction, as we see. So the luminosity is equal to the variation in energy, internal of the total energy. So if the system is in equilibrium, so it's, there is no accumulation of energy, so energy is flowing perfectly. We actually the variation energy is equal to luminosity, the nuclear luminosity energy produced internally, and the less the luminosity that is that's leaving the stars. So there is equilibrium. So we don't have contractions, no release in gravitational way of energy. We see the luminosity that are escaping from the surface of the stars should be has to be the same the luminosity produced by the nuclear reaction. So that's the reason we can put L here, and below should be put not the mass, total mass, but the mass of the core that is a fraction of the total, put F. And this is another value that is definitely higher. When we manage to calculate the actual production energy per unit mass, it's also useful because you can use it to calculate the fraction of the mass that is inside the core. That is quite interesting. Also, we see that is quite small, usually 10%. A brief recapitulation on what we are talking about. It is useful. Nuclear reaction, we are talking about interaction among nuclear particles. Nuclear particles, we have the boson and the fermions. Boson are the one with the number of the spin that it is an integer, positive, not negative. That means it can be 0 or positive. Typical photons, meson, something that is also not connected with nuclear reaction, that is phonons, but are quite studied in physics. Particle ray alpha. The fermions are the one there with the spin number that is 1/2 and plus integer, so 1/2, 3/2, 5/2, and so on. And they are usually more the other typical particle we see: electron, proton, neutron, and so on. Plus, obviously, their antiparticle. These are the differences among the mechanical statistical. They are ruling them. Boson from the Bose-Einstein distribution, fermions from Fermi-Dirac distribution. Then we have the hadrons, the leptons. Hadrons are the massive particle, leptons the light particle. These are a simple differentiation because of the characteristic in the interaction. Hadrons are mainly actually the ones that are made by quark, and we have the baryons, what we see mainly. They are the combination of 3 quark, like protons and neutrons, and the meson, they are a combination of just 2 quark. Lepton, they are the light ones, the small are the electron, neutrinos, and so on. More small, not part compute made by other particles, but just single particle. Something that is important also to remember: the several rays that, like one century ago, we are talking about alpha rays. They are actually the nuclei of hydrogen 4, helium. Sorry, helium 4. You see the 2 that is the atomic number, 4 the mass number, and 2 plus because it's ionized twice. It's just the nucleus. Beta ray are the electron, and gamma ray are photons, mainly the more energetic one, usually with energy around mega electron volt. Technically, from 0.1 mega electron volt above. They are the spectrum of the gamma ray exactly we talk about them. They're essentially the typical photon produced during nuclear reaction inside a star. This is better. Nuclear reaction, we have several, and we can see several of them also. The main one, usually, when you are thinking about stars, is the fusion. That is, okay, fusing two nuclei together. Two, usually, in some reaction are three, but actually is two reaction among two particles, because to manage to have three particles colliding together is too complicated that it is practically impossible. Another interesting type of reaction is spallation. When the nuclear is hit by a particle with enough energy that and momentum that permit to take away some fragment, or smashing in part in this part. The typical from spallation is the production of lithium, beryllium, and boron, that we'll see that fusion reaction didn't manage to produce them. Sometimes are produced but are then destroyed by other reaction. This is also because lithium start to burn really quickly inside the star, so it's quickly depleted by nuclear reaction. It's not produced. Another type of nuclear reaction induces gamma emission. That is like in an atom, we can have an electron in excited state, excited level, pass a photon and induce an emission of photon, and the electron decay to a lower level. Similarly, can be introduced with a nuclei, with the nucleus inside with an excited level, and the pass of gamma ray may induce the emission of a gamma ray. Alpha decay, that is the nuclei are emitting, losing a part, but not because it's collided, this collision. It emits an alpha ray. Fission, that are the splitting of a nuclei in two or three parts, and the beta decay, they are usually it's when the nuclei have too much neutrons. Some neutrons neutrons are quite unstable, you can see, easily decay. Usually the mean time for in beta decay of the neutron is like 1,000 to 2,000 seconds, if I remember well. And the neutron decay, when you're usually in a nuclear, are really stable because of interaction with the other, but there are too many neutrons that will decay, emitting an electron and leaving a proton inside. These are mainly the type of nuclear reaction, and we have almost everything. Fiction, we have something more than 2-3 parts. We'll see at the end. In the case, we have the photofission of nuclei of iron. They are literally vaporize in helium by really strong gamma ray. And so actually inside a star there is only fusion. Spallation usually sometimes is more outside that inside the star, produced from a cosmic ray produced by stars. Particles are getting around and colliding with other elements producing lithium, beryllium, boron. The reaction usually are written in this way. We have the reacting particle, one main like this, one other that is usually considered one is the target, the other is the projectile. They are colliding on the first one, going in producing two other particles. We can rewrite in this way also, like is parenthesis, the projectile, the secondary particle that is emitted, and the final product y. This is usually because we can have one main particle collided by another one that will produce a particle y, in this case, mainly with a secondary emission B. Easily B is the photon or neutrinos, usually a small particle, smaller than the other. Something that is really important in a nuclear reaction, we have a conservation of several elements, angular momentum, the spin included, among the other, but it's also the spin that is not small, because one element that bring to discover in the neutrinos was that in the Becker decay we have the neutron decaying in a proton and an electron. Luckily, the spin was not conserved because before we have spin 1/2, and the other side we have spin that was an integer, 0 or 1/2, depending on the spin was aligned. That is a problem because it should be conserved. That is one of the reasons of thought there should be a third particle that permitted to conserve the total amount of spin. Another characteristic that is conservation of charge. If the reacting particle in total has a neutral charge, also the product in total should be neutral charge. The charge should be conserved, have to be conserved during the reaction. The rest mass energy that we'll see. Also, actually most of the mass rest is with the energy considered all, that is like also we consider as a part of the reaction, the gamma emitted by the reaction. The baryonic number, that is the number of baryonic particles before and after, these have to be conserved. So if like we see in the reaction with the proton with proton, we have two baryons. So on the other side, we need to have two baryons again, not exactly separated, but the product produced have to be as a total baryonic number 2. Leptonic number, that is the same about the lepton, so you consider the electron and neutrinos. It's the number of particles before and after should be conserved. We mentioned before, I didn't mention it in November said, but baryonic number, leptonic number, remember that the antiparticle is the opposite value of his particle. So if an electron is 1, the positron, that is an anti-electron, is -1. That means also that obviously, technically, for example, if you have, we see production of pair, we have a photon that produce a pair of particles. We have one particle, an antiparticle, so 1, -1, 0, and it's conserved the number.
But isn't that for the charge, or is it only, or is it for the baryonic leptonic number? I'm confused.
All except the mass. An antiparticle has the opposite of the value of the particle, except in mass, that is the same, but as charge as the opposite, if there is charge, obviously. But this is essentially mass counting the characteristic. It's because, okay, the charge, we are considering the physical charge of the particle. So electron has -1, positron has +1. The baryonic, say, is for the conservation, because we have shown that the particle, the type of particle, have to be conserved, the number total. So if you are fusing 2 protons and we get the deuterium, we'll have in the nuclei 1 proton, 1 neutron, but are anyway 2 baryons. So it's conserved. The same is the leptons, but also it's this also has the problem, because if you have, for example, in particle and antiparticle, how we should treat it, and the antiparticle has a baryonic number and the leptonic number is the opposite, as the charge. It's mirrored for also in this kind of computation. That is shown, an example is the production of pair by photons. Photons are quantum, is not a lepton. So as a lepton value 0, but producing an antiparticle, producing particle, the antiparticle, the leptonic number should be 0. In fact, the antiparticle is -1 and the particle 1. This permitted to conserve the number, the baryonic or leptonic number. That actually are not the only one. I put here just plus, that are marginal, but just to know there is the strangeness number, the charm number, the bottomness number, the topness number. These are connected with the presence of several quarks, strange, charm, bottom, and top quark. They are particular, not involved in our nuclear reaction, because mainly we in proton and neutrons are just up and down. But the same, also this characteristic have to conserve, and an antiparticle have the opposite of this number of this particle. Strangeness, just I mentioned, that is a fun fact, that the strange quark, that is the basic of the strangeness, actually has a strangeness number of -1 because of how the strangeness was defined. The definition was before the strange quark was found, and this caused the opposite. It's quite similar to the electron that is actually the main particle for the electricity, for the charge, moving charge, because the electron that is actually moving inside the wire, something, another medium, it is as a part charge value of -1. So when you are a current in a direction, actually the electron moving in the opposite direction. This conservation is not just to put it because it's a class. It's really important. If you are using the conservation, especially of charges, see also for the spin, the mass is important for another. You see the next. The baryonic, the leptonic, you can manage to reconstruct the reaction really well. With a little of thinking, you can, don't have to remember perfectly all the detail of the reaction, but you manage to reconstruct. Usually, you'll see that most of the reactions are quite, some is really simple, like the proton-proton, but the first channel, that is the most famous, the one that are proton-proton producing deuterium, another proton that producing helium-3, helium-3 with helium-3, they are producing helium-4 plus 2 protons. This is the famous PP1, the first channel for the proton-proton nuclear reaction. There are another two that are a little more complicated, but are actually also not minor. But if you want to remember, if you remember these kind of things, you can reconstruct perfectly the several the reaction, because proton-proton are fusing, producing obviously a nuclei with 2 protons is in helium nuclei with atomic mass of 2, it's mostly impossible because the 2 protons are repelling themselves, so it's not stable. So you need to have and that one should be decay in a neutron. If you just have in this way, you see that you have two proton neutron. The baryonic number is conserved, okay, but you see that the charge is not conserved. That means that has to be emitted a positive charge, but the baryonic number is conserved, so cannot be emitted electronic. It can be a baryonic particle, should be emitted electronic in this case. So the plus should be electronic, lepton with positive charge is the positron, the antiparticle of the electron. But in this way, the leptonic number is not conserved. You need another lepton that is neutrinos. And since the positron is an antiparticle, so the leptonium -1, this is to be a particle, so is emitted in neutrinos. In this way, you see, you manage to have all the reaction without memorizing them by heart, then can cause some problem. And believe me, In last time I did the course, several wrongly put sometimes an electron instead of a position, because they are remembering the E, but not remember that it is E plus. With the reaction is not a good idea to try to remember by heart, memorizing them blindly, but it's better to remind some part important and then reconstruct the remaining with the conservation law. Remember that is a conservation of charge, baryonic number, leptonic number. Usually the conservation spin came along because it's the same in concept. The reaction, we can study them as I said, it's the interaction between the two reacting particle, and usually it's a good way to see it as a step, the nuclear reaction. So the two particles are interacting, forming an intermediate composed nuclei excited. See, with this asterisk, that means it is in excited level. That means there's more energy than the low main basic level of the nuclei. And then we have the following result of the reaction, the decay of this excited nuclei in several channels. We can have the emission again of the projectile particle. It is just an elastic scatter. Can be the two, an elastic scatter due to the electric potential. So the particle didn't actually manage neither to enter, just bounce on the nuclei, or an elastic scatter by the nuclei. The particle managed to enter to produce the internal and being thrown away again. It is the first one, not exactly like this, it is not producing the compound nuclei, but different is not so easy to see from outside. So it's almost the same. We can have also an elastic scatter, just the particle A is re-emitted, but the target nuclei stay with some energy and so a little excited. Another is the emission particle. From the compound, it's emitted, it decay in another different nuclei than the X one, and a subparticle is emitted. We can have just an emission of decay of the compound nuclei as energy that is called radiative capture, even if it's emitted radiative, but the name of this type of emission is this one, radiative capture. So the excited compound nuclei decay in energy emitting a gamma ray, or fission when we'll have the split of the compound number nuclei in other parts, and sometimes one part more. This is, for example, the photo disruption of the iron by gamma ray. We'll see that is the nuclei of iron is split in 13 alpha particle plus neutrons. If this one is a channel, a different way the reaction can result. The probability of a channel is given by the energy of the excited the compound nuclei, the momentum, parity, but not how he's produced. If two way produce the same nuclei excited with the same energy, same physical characteristic, the channel have the same probability.
¿Qué era la Y?
¿Mm?
¿Qué era la Y?
It's a product particle. Usually it's the more massive one. In this case, if you consider it proton-proton, they actually here are the same. Here should be the deuterium. In B, actually no, it's not just one, but B in this case will be plus the one because are a positron and a neutrino. But this is a schematic. Usually, for the reactive particle, you have two because it's difficult to have more than two particles. But the product particle can be several. And we saw in the interaction gamma ray with the nuclei of iron that excited the iron, and then this is splitting in 14 different particles. This root. So the product of the reaction can be two or more, usually always two, because if it's just the are fusing two particles, like can be in the case of hydrogen, not, but because hydrogen is just it's not the same number of neutron and proton, but the fusion of carbon oxygen can be the two put together, and so you are producing a nuclei directly, but also the emission of energy like a photon. So you have at least the two particles, the other. Also because for the conservation of momentum. And here the Y is just a particle, the main. Usually there is one particle that is bigger than the other, and that is the main product, and the other is the subproduct. It's a convention. This is also as here, because you can easily write it in this way. With the X and the Y, there are two main particles, the target particle and the product particle. In A and B, they are the two secondary particles in the reaction. A, the projectile one, that are colliding on the X. In the B, that is the emitted particle in the reaction. Then actually it can be the same more. Condition for this description are quite simple, that the mean free path of the nuclei is less than the radius of the nucleus. The mean free path of the nucleus, it is quite obvious, and the energy, excited energy of the compound by for each nucleus is less than the separation energy. It means that you're not giving too much energy and permit not to extract directly. This is a model to describe the nuclear reaction, but it's quite useful because you can have actually several channels from a reaction, and in the calculation of the nuclear reaction rate, you have to consider the several probability of the channel. Then are two values that are quite useful. Is the Q value, that is simply the rest energy of the reacting particle minus the rest energy of the product. That here I'm showing essentially if some of the mass of the reacting is missing. It is simpler, consider it just for particle. Let's say we are considering that we are a main X target with the projectile A they're colliding, producing a Y particle and an emitted B particle. Then it can be more actually, but just for presentation, generally is this one. We can rearrange and see that similarly the Q value can be seen as the mass excess of each particle, the sum of the reacting minus the sum of the mass excess in the product. The mass excess is just the difference among the mass of the particle minus the not exactly the sum of the mass of the is compounding, that we see later, but the mean value. In here you can see the equation. This is just by definition the atomic mass is more or less exactly the baryonic number of the reaction, so this is 0, and this is cancelled. This is the Q value is actual the energy released by the reaction. We at the beginning we have the two particles have a certain mass, and the end have less mass. Some mass is lost. This mass is because the internally the nuclear are rearranged in going to the lower state of energy. So they release some of this energy that the famous E equal m to the c square is not just the rest mass, but is in actual relation between energy and mass. Energy is a mass, and the mass is an energy, and you can see really well inside in the nuclear reaction, in the fusion, because we have in the fusion use perfectly two nuclei that are fused together, not decay. The particles remain the same, but at the end the mass it's lower because actually it's the boundary energy that is going down. So it uses lower energy, and this energy is emitted like a photon. These different are given as important because the Q value are tell us if the reaction is reducing energy or are absorbing energy, exothermal or endothermal. It's if the Q is positive, the reaction is release energy, and this permits to maintain the system and the production of the continues to have a nuclear reaction. If we are taking away energy, so the particle emitted at less energy, so are cooler. That means they are taken away, so the system, the reaction are against the production of the sustain of the nuclear reaction. It is the second, it's a classical for the production of iron that are not releasing mass energy, so are cooling the core. And from here, we can help it with the binding energy, that is actually the energy that is releasing information of a certain nuclei. If we are just as it will be in fusion, taking all the proton, all the neutron, and putting all together, and producing this way of this nuclei. This Q value is called B, binding energy, and this the energy that is released, that essentially the difference in the mass from the initial part, the single particle and the nuclei putting all together. Mainly, it's use the binding energy divided by the atomic mass of the nuclei, the number of nucleons that are inside the nuclei. This is also, you can see here the graph, but maybe we can see here. No. The binding energy by per nucleus at this shape, it is from 0, that is okay, the binding energy of a nuclei of hydrogen 1, that obviously is just a proton. So you have the proton and the reson is the proton, the different mass is 0. You see they are increasing, are little change, little fluctuation, is not perfect. Arriving to the maximum, that is for the iron, that is essentially the more stable. It is more or less 8.5 mega electron volt per nuclei, and then again decrease. I'm showing here this shape is not exact, is not similar to a hyperbole, that is the inverse of the number of nuclei. This is also mean because of the actual number, then binding energy is increased constantly. The atomic number of the elements. Going what?
But shouldn't, if it's binding, shouldn't it always be fusion? If it's binding energy, shouldn't it always be fusion? Like binding is putting two things together, right? Why is there fission there? I don't understand. I'm confused by the use of words.
The binding, because is the energy to bind the nucleus. The binding energy is essentially a Q value of the creation by its basic particle of the nuclei. we are taking, for example, the binding energy of an helium is we take two protons, two neutrons separated, we put together magically because it's not easy, and we'll have that in this way, before the four particles have a mass, total mass, actually, and rest energy. At the end, the helium nuclei have a different and a little lower rest energy. It's different in energy is the binding energy, because when you are combining the four particles, they are binding together, are going in low energy state, and this decay in state causes the emission of energy that in this case will be a photon, but the release energy is the energy that is bounding the three particles together. You need to give to the nuclei this energy to split again the four particle and the four nucleons separated. It's how stable can be the more is the energy, the binding energy by nucleon, and this kind of energy for each nucleon.
Okay.
It's you can see that the energy released to when we are putting together the nucleons to form the nucleons to form the nucleon. It's you see that if the nucleons are pairs, each one have its mass, protons and neutrons. But if you weigh a nucleus, we see that have a mass that is a little lower the initial mass of the particle together. This is because when forming the nucleus, the particles are interacting, binding together with a strong nuclear force, and going in the lower energy state, and going are emitting energy that is the binding energy. That the binding energy increase constantly with the element, with the atomic number. So each element has usually a higher binding energy of the previous, but if divide by the number of nucleons, the atomic mass, that is A, that technically is an integer. If you are looking in the periodic table, you see the atomic mass, it's not an integer, a fraction. This is because it's not the atomic mass of the nuclei, but a weighted value for also because it's considered the number of consider the mass of the electron, but it's weighted among all the isotopes of that type of element. It's then also it's the atomic mass. Actually, it's in unit of based on the atomic unit, so a little different from the number of small, but in first approximation you consider the same. If you divide the binding mass, the binding energy by the number of nucleons, the result is that I have this shape that increases from one side and decreases from the other side. The decreasing part on the right is due to the Colombian repulsion. We are more and more protons that are so the interaction among them is stronger. They are trying to disrupt the nuclei. On the left part is due to the surface tension of the nuclei. This is because when you are forming at the beginning, when you're forming the nuclei, mainly the particles stay on the surface. You see quite easily, the deuterium are just two particles, so stay more nearby the surface, and helium-4 are arranged, all stay nearby the surface, and the nucleons near the first surface is less bound than nucleon inside the nucleus, because inside they are connected, interacting with more nucleons. So at the beginning, it's easier to put it together. So we have this increase, and then due to the Colombian, it's decreasing again. Mainly, it's used as say that the binding energy for nucleons. This is also for a reason that there is a connection between the Q value per nucleus of the product of the the total. I put a Y, but it's the total, and of the other two. Essentially, if you are considering the relation, simple relation, when the two interacting particles are the same, the target and the projected particle are the same particle, and just emitting a photon, simple fusion. In the simple fusion, we have this connection among them. Homework from Friday or also Wednesday. It's quite simple, just need to take the time. You see that is calculating the Q value according to the binding energy by nucleons. You see there is a relation. Actually, it's a difference. You take the result of the fusion and the binding energy of the rest of the fusion. You subtract the binding energy for the nucleus of the reacting nucleus, and the difference are giving you the Q value, the energy released per number of nucleons. So easily you can see here, when you are producing iron, you still have a little production of energy. Yeah, it's clear. But if you try to fuse the iron, going up here, you have the binding energy is less, so difference is negative. That means the reaction have a Q value that is negative, is not more exothermic but endothermic as absorbing energy. That is what caused the collapse in we see in a massive star that producing the supernova. The core trying, but it's absorb energy, so immediately rapidly the luminosity, internal luminosity is turned off and the star is not sustained. Just for curiosity, you can divide energy per nucleus up in megaelectron volt actually has a formula, a semi-empirical one. Here it's written the value of the parameter. This is 14, 13, 0.6, 19, 33. With several, you have a basic value. Then the first one that is the surface tension that you see why have this value. This is because it's connected from the relation between the area of the surface of the nucleus and the volume of the nucleus. And you see the sphere, the area is 4p for the radius to the square. The volume is 4p divided by 3 for the cube of the radius. So it's essentially the inverse of the radius. Since the radius is the third root of the volume, and the volume is proportional to the number of the nucleons, you have this relation. The second term is the Coulombian repulsion. Then there is this factor that taking account n is the number of neutrons, z is the atomic number, the number of protons. That considering if there is a difference, this is because just the interaction between among a neutron and the proton is more stable and more stronger than an interaction among neutrons and among protons. They like to stay more together among neutron and proton than the other. So if the difference, you are changing. And then parity correction doesn't matter. Interesting are these two parts. They are the interaction given by the Coulombian repulsion and surface tension to explain these two parts. Okay, soon we'll. Yeah, okay. Some we'll see better later. But something that is really important is to estimate the rate of the neural reaction to see how much is reaction producing. This for two reasons. One is the rate with the Q are giving us the energy produced by the reaction. So the famous epsilon. So we calculate how much energy are producing or actually comporting with the luminosity we saw. We can understand also how is bigger the core. Then also to understand the problem and the consequence of several conditions on the reaction. how the rate depends on the several physical properties like density, temperature, and how it's changed. As normal, that we consider the usual particle X target a particle producing a main particle Y with emitted particle B. I have the two particles we are considering in the relative velocity, the velocity of the barycenter. The classical here M is the reduced mass. I put M should be actually a mole because usually the reduced mass is indicated with mu, but since with the mu is already used for the atomic mass, not that too much confusion. It's quite typical in elaboration like astrophysics, where putting together several branches of the physics that are redundant use of some letter. And but some starting to describe. Just remember a typical temperature inside the star for the nuclear reaction are 10 to the 7, 10 to the 9 Kelvin. That means energy are not so high, just 100 kiloelectron volt. That is quite low, actually, if you consider that, for example, every particle accelerator here that we are using have energy of mega electron volt, lowest, but usually are actually not giga electron volt, tera electron volt. The larger hadronic collider, it's a tenth of a tera electron volt. Going on the next step, going to be near peta electron volt. That means also that energy you can see we'll see tomorrow, but you can see that is quite probably some problem because the kinetic energy of the particle are small than mega electron volt, while we saw the binding energy for nuclei are of mega electron volt, several electron volt. So we are like 100 times the kinetic energy. So we'll see that obviously that will be some problem to permit the projectile particle A to enter in the nucleus of X. Last things to start to see everything, but well, let me see. The rate of the nuclear reaction is just as we already saw, the integral along all the energy, all the velocity. I have to check here in the number and density it is not convenient. In velocity of the relative velocity, multiply the cross section that depend on the relative velocity and the numerical density of the particle. The cross section can be seen as defined as the number of interaction. But now I see interaction, non-direct reaction. By divided the number of the target particle for a unit of time, divided the number, the density, the number of nuclei here, or the density of the nuclei here the same. It's equal if you put, the important is the same, because since are the one by the other. Oh, not but is no, it's the numerical density here in the nucleus and the numerical density of the projection divided by area divided by the time. And here it's cancelled. Here no, it's put together. In fact, you have to multiply by the density number. The cross section is classically should be like the size of the particle, the area of the section of the particle, you can see it. So how much how easy is to eat it. For particle is not more this way, because a particle has no real dimension, physical or geometric, but is the cross section is actually the probability of the interaction, the probability of the collision among the target particle and the projected particle. In general, we consider Maxwell-Boltzmann statistic, classical in this way. You can, with here the energy is put in kinetic energy in isotropic distribution. Maxwell-Boltzmann can be used without problem, because since we are considering reaction among nuclei, so ions, the ion degeneration arrives at really higher density, like 10 to the 14, and we are the center is 10 to the 3, so it's not so dense. Also, when we are going high, we have higher density, we can have the degeneration of the electron, but not the degeneration of the ions of the nuclei of the element. The next we'll see tomorrow. Any question?
No, solo tengo que leer. Estoy un poco atrasado con el estudio, entonces tengo que ponerme al día con algunas cosas.
Anyway, I'm recording this lesson. Now it's a recording from the beginning. Since the university asked to, I don't understand exactly if they need to be record anyway, or just if you are missing someone. But arrived yesterday a mail from the vice rector of the academy, and he's around. Please do this, and he's also asking to should be recorded to permit you to missing student to see the lesson, and I'll see, probably I'll put in YouTube, I don't know. Okay, the previous lesson are not much, I don't know how much problematic it can be. Now it will be a little more tough matter than the previous.
Professor, do you know already what's going to be in the following test, on the first test?
The first test, more or less in a month, 4 weeks, because I was estimating to see how it will be. We cover little less than half in 3 weeks, so probably this part of the nuclear reaction that we'll see this just taking take one class for the introduction. probably take another for weeks, and there will be. Considering the unusual situation, that also that is it's useless. Say I cannot check you easily. But also, if you ask to open the webcam, the adjacent part is not like in a class where I can check you are not reading something. So I was more thinking if written exam, when you have to not simple question, something you have to write to explain the things. In this way, since I cannot check if you are using notes or something like that, at least even if you are using it, you need to put use your mind to elaborate the notion, to put the notion on written, and I'm sure that that concept will remain in your mind, and you will remember the important things. That is essentially because the exam mainly is to certify that you understand what you are talking about, that you remember these things. It's, in this way, if you are you're doing well, it should be that you are you remember and you understand this part of the problem.
Thank you.
Not at all. It's in fact as was also asked as you already presented some part of the DRA asking to describing exam the date, but also said that the problem there is no still is not in the system. So in fact I wrote yesterday saying please it's still not there. Also we needed to know because it's the course is there is the course or not, because it's at the end the course is not in the system, is useless to do exam if you cannot put the notes, the score in the system. And also you have to know it makes sense to follow the classes or not. Okay, you have any question? But anyway, I'll see to load again to load the class so you can look at it again.
Thanks.
Okay, no question. See you.
Yeah.
See you tomorrow.
Sharp.